Well, welcome. Now it's time to start the last part of AP Calculus BC. And that's an area called Taylor polynomials and Taylor series and power series. And so we're going to look at the first topic, AP topic 1011, and that's Taylor polynomials today. So let me try to set up the idea like this. Let's suppose that we have a graph, and the graph does something maybe kind of interesting like this. Okay, if we let's make some random points here. 1, 2, 3. So we have some x coordinates, some y coordinates. Okay, let's say that we know that at x equals 1, y, or the f of x equals, let's say, 1.2. That's something we know. But let's imagine that for this function, that's the only thing that we know. Well, in calculus, we have found other ways to estimate what might be happening near x equals 1. One of the first things we did, or one of the first ways we'd estimate an AB, calculus AB, would be called a linear approximation, where we know the slope, we find the slope at x equals 1, and then we know that point at x equals 1, and we are able to estimate, maybe kind of nearby what another point would be. But we see that with this linear approximation, once you get very far from x equals 1, this part right here in orange, our approximation can get pretty far away from the actual value that we're trying to figure out from f of x. So then in Calculus BC, we learn another method called Euler's method. And so Euler's method lets us look at the slope right there at x equals 1, go a little bit beside it, and then estimate maybe the slope at that new point, and then estimate the slope at that new point, so that we're able to at least get a closer approximation. But Euler's method still does not work very far away, and it's just not good on graphs that have a lot of curvature. So this really is kind of the foundation of what mathematicians were trying to figure out. They're trying to figure out how to explain things like graphs of e to the x or sine of x, and how to demonstrate those with algebra. And so what I want you to think about is let's go back to our first linear approximation here for a second. That's, okay for something that is really close to x equals 1, but it gets really, really far away the farther we get. But what if we could, instead of a linear approximation, what if we could come up with a quadratic approximation? So now, instead of a straight line, what if we could come up with some kind of parabola to approximate f of x? Well, there in red, there I've created a parabola, and we see that actually for this blue line f of x, a parabola does a really nice job and gets us really, really close to the values of f, at least for a while. But unfortunately, our f of x has a second curve, and so our parabola doesn't really help us after that second curve. But we see that by adding a power, going from a linear approximation to a quadratic approximation, we have gotten a lot more values that are close. Well, let's just keep taking it a step further. Why not do a cubic approximation? Well, now in this case, if my blue graph is an actual cubic graph, then my cubic approximation would just nail the exact value, right? And so that's pretty cool. Now it's not an approximation anymore because it is, it's exact. And so what calculus people were really interested in, mathematicians were really interested in, was, what happens if we keep adding powers to our approximation? So now, we'll have a fourth power function and then maybe a fifth power approximation function. And that should help us to get closer and closer to some pretty complex graphs. And so finally, if we have, maybe think about the graph of sine, then just kind of going forever and ever and ever, where we want to go is, well, what if we could approximate right here at 0, 0, and what if we could approximate never-ending polynomials that the curves just kept going? If I just do so many degrees, then in red eventually I'm going to break away from sine. But if I keep doing more and more degrees, we're going to end up matching up with sine. And so that's what we're going to look at. We're going to look at something called a Taylor polynomial, which is a polynomial. Just think back to algebra, is just a set of different terms added or subtracted, and they all have different powers. So we're going to look at different Taylor polynomials to different degrees. So like we will want to talk about, a fourth degree Taylor polynomial would have 5 terms, right? X to the fourth, x to the third, x squared, x, and a constant. A third degree Taylor polynomial would have 4 terms. Or I could say write a 3-term Taylor polynomial. That would be an x squared, x, and constant. And so that's just, a Taylor polynomial is now, instead of a line that approximates some function, we are trying to get more curves on our approximation. Now, before we start reading through the what you must know and doing an actual practice problem, let me point out one more thing, that it really, really matters where you're starting. So look at this point right here that I started with. I said we know at x equals 1, y equals 1.2, and then we were creating all of our curves, our straight linear approximation, or we were creating our actual quadratic approximation that looks something like this. We were creating all those at that point, right? That's the point where we know, so our approximation line passes through that point. That point is called the center, and we will usually let that be C. So in this case, C equals 1. So center just means the place where you are putting your approximation line on the original function and then estimating from there. Okay, so we have some stuff to learn. You have a basic idea of what's going to happen. So here we go. A Taylor polynomial, p sub n of x, or sometimes you'll see t sub n of x for Taylor, is this function that you have to memorize. Now, it looks really overwhelming, but there is a pattern. The first term, if I want a first degree, that'd be a constant, so it's the function at your center, whatever they tell you the center is, divided by 0 factorial. Now, we should take a time out for a second and make a note that 0 factorial is defined as 1, and so there you go. You can Google all the reasons behind that if you want. So then, if we want a Taylor polynomial that is 2 terms, we will then add the first derivative at c divided by 1 factorial, which is just 1, times x minus the center, c, to the first power, and that gets us our x power, right? That'd be a linear approximation. We'd have 2 terms, a constant and an x to the first power. Then if we wanted a third term, we would take the second derivative of c divided by 2 factorial, and then go x minus c to the second power. That'll get us a quadratic approximation, and then so on and so forth. So however many terms you're asked to get for a Taylor polynomial, all kinds of whoopses. However many terms you're asked to find for a Taylor polynomial, you are going to find the derivative of that number of terms, that degree, whatever degree you're asked to find actually, divided by that number factorial, all taken of the center, and then times x minus the center to n power, whatever degree you're asked to go to. So this is a formula you're going to memorize and use over and over and over again. So commit it to memory early and try to do the work from memory. And you'll see an example of this put to use here in a few minutes. Now, several notes, and these are notes that you might find yourself needing to come back and read over the next few lessons as you're trying to put your mind around what's exactly going on here with Taylor polynomials. But C is called the center. Okay, we saw that in our picture of the graph. It's the input point where you're matching your polynomial approximation to the actual function. So you will know it. It'll give you an x equals a number, so that'd be C equals a number, and you will actually know that. You'll be told we're going to center this at 4 or at 1 or at 0. Now, so then x represents a value that you want to plug in to find an approximation. So all of these x's up here would be like if we want, let's say that our center is 1, so then we want to approximate maybe at 1.1, right? We want to approximate close to it. Or maybe we want to approximate farther away from it, 1.5. But it usually will be close to the center. So x is your approximation number that you're shooting for. So n represents, it's stated wrong on here, and I'll fix it. It represents the derivative that you are finding to. So if you have an n of 5, you're actually going to have 6 terms, okay? And so it'll be you're going to the 5th derivative. So note though that each of our terms changes 3 of our n's. We have a derivative power that changes, that gets an n, a power on the x minus c gets an n, and the factorial gets an n. So up here, so n, well, just look at the general term here. You're taking the derivative to the nth power, you're dividing by n factorial, and then your x minus c is to the nth power as well. We'll see all that in a problem here in a few minutes. Note already, 0 factorial is 1. And note that we will write or evaluate Taylor polynomials to a certain n. We aren't examining these polynomials to infinity. Now that's a big break from everything that we've been working on with series so far. Right now we're not using the word series. We are going to stop at a certain power or a certain number of terms, however the question asks it. So, for example, p sub 5 of x means write out the polynomial to the 5th derivative, you'll have 6 terms. Now sometimes terms have the number 0 on them, so they cancel out or they disappear. Okay, so big picture for a second. You're going to memorize this formula, and really you're just going to memorize the pattern that happens over and over again. You'll be asked to find it to a certain degree or a certain derivative, that will be your n, or a certain number of terms. So your n will be 1 less than that because your constant term counts as 1. That'd be like a degree of 0. Then what we're looking at is we have a center number, a number that we are approximating, that we are connecting our approximation model to the actual function. So the center is something we know. We are approximating our model at a number x, which is usually close to the center. And we'll be told how many terms to do. Okay, so a few notes, a few things to learn, and then we'll practice one of these. First of all, oftentimes, not often, maybe often, but a lot of times, we'll let the center be 0. So x equals 0, so the y-axis. So we're comparing our polynomial to the actual equation x equals 0, and we'll call that c is 0. When this is the case, the Taylor polynomial is called a Maclaurin polynomial. Now Taylor's one mathematician, Maclaurin's another one who worked years later after Taylor and learned a lot more and did a lot more with Taylor polynomials, and just gets so what Maclaurin's work was important enough that now any Taylor polynomial centered at 0 is also called a Maclaurin polynomial. On the AP exam, it could call it a Maclaurin polynomial, then you know C is 0, or it could say a Taylor polynomial with centered at 0, or it could say a Taylor polynomial about 0, or something like that. So any of those all mean the same thing. A Maclaurin polynomial is the same as a Taylor polynomial, except C is always 0. In a Taylor polynomial, the center can be anywhere. You can memorize a new equation for the Maclaurin polynomial, which I think is probably a little bit of a waste, or just memorize the Taylor polynomial and plug in zeros for all your C's. And so what happens is up here on the Taylor polynomial, every time you have f of 0, you're going to be evaluating the function at 0. And then instead of x minus c to the first power, you're just going to have x to the first power. X minus c to the second power, you're going to have x to the second power because c is 0. All right. Now, let's talk about how to write out these polynomials, and this is what we'll practice here shortly. So to write out a polynomial, you will have to calculate each term's derivative with your C input, with a C input. This means that you might have several lines of work. Sometimes this takes a little bit of work. Sometimes you're given a function, you have to figure out the derivative for each term, and then you have to calculate C for that derivative, and then that ends up going into all of these f of c's, right? F of c, f prime of c, second derivative at c, third, fourth, fifth, however many derivatives they ask you to find. Every single term is going to have a new derivative at c until you reach the whatever term it tells you to stop at. So that can be a little bit of work, okay? Now, we might want to use our polynomial to approximate a function at a certain value, and so then you'll be told how many terms to use, what number to plug in for x, what number you're going to approximate, and where the polynomial is centered at c. And again, if the instructions tell you to use a Maclaurin polynomial, you know c is supposed to be 0. And finally, you might be asked to do any of this, write out a polynomial, or use it to approximate by being given a table of values. This should actually make your work easier because the table will list the term's derivative value. You don't have to actually calculate it. Okay, so I've given you a lot. I feel like that's a lot of stuff. Let's work out an example together. And I'm just going to just warn you that you have to practice this. Like, this isn't something that is supernatural for us, right? So make sure that you are practicing this, that you're giving it a good shot. Okay, so let's do this. Let's just start off with a function, and a lot of times these will be transcendental functions. They won't be like just regular polynomial functions because we don't need to approximate those. Like if you have a cubic function, you can just come up with a cubic Taylor polynomial, and that's the exact model. It's not an approximation anymore. So we like to use sine, we like to use cosine, we like to use e. Let's do e to the 2x. So let's say we have a function e to the 2x. We're going to be centered at 1. I want you to see what that's like. And or it'll say centered about 1, or about, it might just say about 1. That all means centered. And we want to write the third degree Taylor polynomial to approximate, to show the approximation polynomial for this function. All right, so if we're going to go to the third degree, then that means that we're going to end up going to some kind of a third derivative. Okay, so here's what we do. We just want to do some groundwork first. So we know the function at x is e to the 2x. So then let's go ahead and evaluate that at our center. Okay, so e to the 2 times 1 is e squared. Now, why am I doing that? Because up here in our formula, the very first thing we're going to write is the function evaluated at the center divided by 1. Okay, we'll write all this out in a few minutes, but we're just going to go ahead and figure all these things out on top. The function evaluated at c, the first derivative evaluated at c, the second derivative evaluated at c, all the way up to the third one, because that's as far as we're asked to go in this set of instructions. So now let's find out what the first derivative of our function is. We'll drop down the 2 e to the 2x. So now we're going to evaluate that at c. See, let me highlight centered at 1. So we're plugging 1 in. We'll do that a few more times. So, whoops. So that's going to be e to the 2 times 1 again. And that's e squared. Whoops, we have a 2 in front of it. 2e squared. All right. So now the second derivative of our function, drop another 2 down, 4e to the 2x. So we're going to evaluate. I didn't put a 1 mark here. I just added this here. If you're watching and writing these notes with me, a 1 mark there. So now we want to find the second derivative evaluated at 1. That's 4e to the 2 times 1, or 4e squared. And now we want to find the third derivative. Now at some point you'll have to keep writing little hash marks. You can write f superscript 3. So that would be drop down another 2, so 8e2x. So the third derivative of 1 would be 8e to the 2 times 1, or 8e squared. Okay, what did we just do? We found 1, 2, 3, 4 answers for our function, the first derivative of our function, the second and the third derivative, all evaluated at this center 1. And that's what's going to go in this first part of our, all these top parts of our Taylor polynomial. Now, what goes underneath it? Well, on the original function, you divide by 0, factorial, 0. The second one you divide by 1, factorial, which is 1, then 2 factorial, all the way up to 3 factorial, and you keep going. Then beside it, you multiply by x minus our center to whatever power you're on. There is none here because it would be x to the 0 power, but then this will be x minus our center, x minus 1 to the first power, x minus 1 to the second power, like that. And so that's how we're going to write this Taylor polynomial. So here we go. We're going to say a Taylor polynomial third degree of x is, okay, here we go. Our first answer, e squared over 0 factorial, 1, times x to the 0, right? There is no x there. I'm going to write all this out. You probably would skip that step. Then our second term is the first derivative. So 2e squared over 1 factorial. Let me rewrite this first one as 0 factorial just so you can look up above and see how this is going in. And technically, I'll rewrite this x to the 0 as x minus 1 to the 0. So you see that we're plugging in the center. So then this will be times x minus 1 to the first power. Then our third term will be the second derivative. So we'll say 4e squared over 2 factorial x minus 1 to the second power. And look at the instructions. It said write a third degree Taylor polynomial, so we need one more. So we'll say plus our third degree is the fourth term. I did green twice there. 8e squared over 3 factorial x minus 1 to the third power. Now that's okay. It's not really the cleanest answer. So our third degree Taylor polynomial will this is all e squared because remember 0 factorial is 1 and x minus 1 and 0 power stays 1, plus 2e squared times x minus 1. And then you can divide 4 divided by 2 factorial, 4 divided by 2, so 2e squared x minus 1 squared. And then 3 factorial is 6, so 4/3 e squared x minus 1 cubed. And that is the Taylor polynomial written to the third degree of the function e to the 2x. Now, a few things. That's interesting and all, but we might be asked to do something with this, right? We might be asked to approximate when x equals 1.1. So then we would just use our Taylor polynomial and we would plug in 1.1 for all of our x's and get a number answer. Now, a couple more things you might do with this. You might actually be told to use a calculator and find out what e to the 2 times 1.1 is, right? We're approximating, but we can use a calculator to find the real value, so that's not super exciting, but this is going back in time in calculus before they could have calculators. So then we can find out, how far away is our approximation from the real value. We'll do more with that specifically coming up in the next lesson. And then the other thing I want to point out that's really important is that we're centered at 1 here. We very easily could have been centered at 0, or the instructions could have said this is a Maclaurin polynomial or something like that. And then all these x minus 1s would become x's because it would be x minus 0. So just put x's in there. So you'd have an x squared, and an x to the third. And then all of these functions and its derivative evaluated at 1 would have all been zeros. So we would have plugged in 0 for all of our functions and would have gotten vastly different answer because that 0 would have changed a lot of things. So that's the big deal. Now there's another thing I want to say, and then there's one more example I want to give you because it's really important that you start to see this second example. But the other thing I want to say is that you might be given tables of values, especially on multiple choice questions, and maybe even some free response, that has a lot of this work already worked out. So just recognize sometimes they'll give you these, or like I've seen on one recent AP exam, they'll give you a couple of these, and then you'll have to find the second derivative or the third derivative by actually finding the derivative of the first one or something like that. So there could be some different variations of that. Okay, I do want to do another one because sine and cosine create some patterns that are going to be really important, and I want to start to set it up for you. So I'm going to say the instructions differently. Let's find 4 terms for the Maclaurin polynomial. Maclaurin, I think is how you say it, of sine of x. So what do we know? We know that our center is 0, our function is sine of x, and I want to find 4 terms. Now, normally we'd think, okay, 4 terms, that's the constant's 1 term, that's going to be 3 degrees. Well, not quite on this one, so let's figure out why. So let's start with the function of x, sine of x, and then let's go ahead and evaluate that at our center, right? Our center, sine of 0, which is 0. Okay, no big deal. So now let's take the first derivative of x, cosine of x. So the first derivative at 0 would be cosine at 0, which is 1. Okay, that's nice. And let's do the second derivative of x. Now we're back to negative, but sine of x. Second derivative is 0. Negative sine at 0 stays 0. Third derivative of x, negative cosine of x. Third derivative evaluated at 0. Negative cosine at 0, negative 1. Now, here's what our intuition tells us. We're going to stop because we only want 4 terms. But here's what you need to see. 2 of the terms become zeros, and those are not going to be terms because they're going to cancel out. Remember, all these values we're finding, let me go up to the top of the screen. All these numbers we're finding are the tops of all these fractions. So whenever we put 0 in for one of those, it cancels out the whole term. And so whenever it asks you for 4 terms, those don't count. So we actually need to keep going. Now, you recognize sine and cosine derivatives just keep doing a pattern. So what I'm going to notice is, see, that was sine 3. I don't need sine 4, because because that's going to be 0 again, or the fourth derivative. So now the fifth derivative is going to end up going back to the first derivative. It just cycles back through. So the fifth derivative at 0 is going to be 1. I don't need a sixth derivative. That cycles back to 0 again. And then finally, I'm going to get my fourth term on the seventh derivative. So the seventh derivative at 0 is going to cycle back to the third derivative and be negative cosine of 0, negative 1. So it took me actually 7 derivatives to get 4 non-zero terms, right? So now we're going to put this into the Taylor polynomial centered at 0. So, well, here's the problem. The first answer, 0, goes in this first one, which is divided by 1 with no x. It's gone. So my actual first number was a first derivative number. That's going to get multiplied by x minus c to the first power over 1 factorial. So here we go. Let me see. Let me write this out for you so you can see what I'm saying. So we want the Maclaurin polynomial, and we're going to go 7 terms, we decided. And what happens is that first one's all 0, so we're not even going to include it. So now we have, I'll write plus 1, so you can see I left off that 0 term, 1 over 1 factorial times x minus 0, my center. Okay, my center is 0. And then we'll go to the next term, which is 0. Okay, right? So then my third term is minus 1. Not my third term, my third derivative. Over 3 factorial x minus 0 to the third power. Because right here, this minus 1 was my third derivative. So n goes, on evaluating the function's derivative, it goes on factorial, and it goes as the power by the x's. And then the fourth derivative is 0. The fifth derivative is back to a positive 1. 5 factorial x minus 0 to the fifth. Sixth derivative is 0. And then the seventh is back to a negative 1. Minus 1 over 7 factorial x minus 0 to the seventh. So we're going to clean all this up and say 4 terms of a Maclaurin polynomial would be 1 over 1 factorial x, so x, minus 1 over 3 x to the third, plus 1 over 5 factorial. We don't have to evaluate that or simplify that. X to the fifth, x minus 0 to the fifth, minus 1 over 7 factorial, x to the seventh. And what I want you to see here is this pattern. Whenever we did an original function of sine, we went every other derivative. And it alternated. Oh, get a little bit of alternating series stuff going on from a few lessons ago. And cosine does the same thing. So as you work on sine and cosine in this unit, you're going to encounter that, and that's going to lead to something important you'll memorize in a few more lessons. Okay, there you go. Remember, we are creating curved lines of varying degrees to approximate other curved lines, eventually really wanting to approximate transcendental functions. And we're starting today with what's called a Taylor polynomial. You want to memorize this box. Mainly, you're going to want to memorize the general terms so you can calculate each of the other terms from it.